have come out of the classroom. If you recall, the last class we were discussing about elevator control power. Okay? See, this is the horizontal tail, all this surface, and this is the elevator, which can go down and go up. And we were talking about what is the elevator control power. And in that we have started deriving the expression for CL delta E and CM delta E. Let us understand what is CL delta E, what does it mean. Remember, if elevator positive angle is deflecting downward like this, as it goes downward, you could see this takes a shape like this, and this almost is like as if it has changed the camber of this symmetric aerofoil, and because of that there is additional lift, and that lift will give a moment about CG, that is the CM contribution. Because of this change in the camber, or because of change in the elevator deflection from here to some positive value, there is an additional lift, and that additional lift per unit elevator deflection is called CL delta E. And because of CL delta E, because of this force, there will be a moment about CG. In a non-dimensional form, we call it CM delta E. So this is a very important elevator control derivative, both CL delta E and CM delta E. More specifically, CM delta E, we call it a strong derivative. Depending upon the value of CM delta E, your delta E required to trim the airplane will vary drastically for a given static margin. Okay? So this is what you should know a priori. You should create an image in your mind how to interpret CL delta E and CM delta E. Okay? Fine. I'm repeating the same explanation using Sinus 912 motor glider. Concentrate here. This is the typically T-tail configuration, and you could see this is the horizontal tail from here to that side, and this part is the elevator. If I put it down, what happens? You see, initially it was symmetric completely like this. As I put it down, it is like it has generated a camber, or we say the zero lift line has changed. That means if it is symmetric, zero lift line will be along the chord. So if there is alpha equal to 0, there won't be any lift. But when I put the elevator down, I now, even for alpha equal to 0, there will be a vertical force. In non-dimensional form, we call it delta CLT. And why that is happening? That is happening because there is elevator deflection. And in one way to explain it, that zero lift line now has changed. Okay? But to us, when we talk about CL delta E, what we are looking for is how much delta CL is increased because of elevator deflection. And that CL delta E, how much that will contribute towards moment about center of gravity is what is CM delta E. Okay? So these two control derivatives are extremely important for longitudinal control. And we will again go back to the classroom and revisit its derivation and try to know how to calculate this thing from the ab initio. Okay, thank you. In the last class, we have been writing so many equations, so many expressions, and the blackboard was full of expressions which I personally never like. The blackboard should be so dirty. So let's come back. We will take out the neat part of it and try to understand it in a better way. Okay. The most important thing what we talked in when you are discussing control, elevator control, we write elevator control, we talk about two derivatives, CL delta E and CM delta E. So let us again revisit and try to physically understand what are the CL delta E and CM delta E. As per the definition, this means change in CL of the whole airplane because of elevator deflection, keeping other thing constant. What is CM delta E? This is change in the pitching moment of the whole airplane per unit deflection of elevator, keeping everything constant. Right? Now let us see what is the mechanism. If this is the horizontal tail, which is symmetric, and this is the elevator, and one way to understand is in flight mechanics you'll find we define something called zero lift line. That is, what is that line along which if the flow comes, there won't be any lift? Obvious, since this is symmetric, if at alpha equal to 0 flow comes, so there won't be any lift produced, right? But now see what happens. If I give a deflection, this is a positive elevator deflection, which we have agreed, positive is down, so delta E positive. Then one way of interpreting is as if the zero lift line has changed. Okay? Because now at alpha equal to 0, there will be a lift, and that will happen because of elevator deflection, and that additional lift will be only because of the elevator deflection. This is one way to explain. So we say zero lift line, this is zero lift line is now at an angle. Another way of explaining it, it has changed the camber. The deflection of elevator has changed the camber of the aerofoil. So you know for a cambered aerofoil wing, at alpha equal to 0, there will be lift. So there will be a CL. So we now understand one thing. The moment I give an elevator deflection, it will generate additional lift. And now what is dCl by d delta E? It means what is the net change in the CL of the airplane because of delta E, or because of deflection of the elevator. The delta CL is CL of the whole airplane. Okay? So one thing we understand, when I deflect the elevator, then the CL of the whole airplane gets modified because there is an additional CL is coming from the tail. Because wing CL remains same. So that additional CL coming because of delta E deflection, let us find it out. Okay? Let us now see, because of elevator deflection, how much additional lift will come on the tail. How much, because of this deflection, how much additional change will come on the tail in terms of lift. I denote it as delta LT. We know, by now we are expert, we'll write half rho v square dynamic pressure at tail into S tail into CL tail. Okay? This is the additional change in the lift because of elevator deflection. Okay? Now we want to find out delta L of the whole airplane, so I have to convert this with the same reference as the reference area and dynamic pressure free stream we are using for defining for the whole airplane. So I will delta L to delta CL. When I want to do, I have to divide this term by, so this implies delta CL equal to half rho v square tail S tail CL tail divided by half rho v square free stream into S reference. Okay? So now this I can easily write as neta ST by S reference into CLT. So what I'm getting? I got an expression delta CL equal to neta ST by S into CLT. Let us again revisit here. What is the delta CL? It's a change in the CL of the whole airplane. Because of what? Because there is some change in the elevator deflection. Right? What is this S? S is the wing area, which is the reference area for the airplane. Right? Once I know this, okay, this delta CL is neta STS into CLT, but do not forget this CLT is additional because of delta E deflection. Right? So appropriately if I write, I should write delta CL, change in the CL of the whole airplane, is neta into ST by S, and the CLT, I should know that this is, to be very precise, I will also use delta CLT here. So these are both the things are same, only I can put it delta also here to stress a point that this is the change in the CL tail because of change in the elevator deflection. Okay, additional thing that has come. So now what happens? This I write neta st by s, and delta CLT I write as dCLT by d delta E into delta E. That is the delta CL. And to be more precise, because this is additional, so I again put delta here. Is it clear what I have done? Neta st by s for delta CLT because of change in elevator deflection, which I am saying delta delta E. Then I am writing dCLT by d delta E into delta delta E. So this gives me what? This tells me neta into st by s, and this I write differently. I write dCLT by d alpha t into d alpha tail by d delta E into delta delta E. What I have done? I have just broken dCLT by d delta E using dCLT by d alpha t by d delta E. What is the physical meaning of this? dCLT by d alpha t? What is dCLT by d alpha t? Very simple. This is CL alpha tail, right? And now second term is d alpha t by d delta E. This is what? This is physically is telling you when I am deflecting the elevator deflection, how much effectively the tail angle of attack is changing, isn't it? And you know that if I try to understand from zero lift line concept, as I deflect it delta E, lift line also changes. So it, or in the camber changes, I can say the effective angle of attack has changed, whatever way you do, right? So this is easily, I can get this term. Let me give a notation as tau, which is called flap effectiveness parameter, which I have already explained. And this can easily be computed by empirical chart where tau is there, which I have explained you, which is SE by ST, where SE is the elevator area, and STL is the total area. This is ST. Okay? So this you can easily find out, and this typical value is 0.4, 0.5 I have told. So now, what happens? From here, I can write delta CL of the aircraft is neta ST by S, then CL alpha tail into tau into delta delta E. So delta CL by delta delta E is dCL by d delta E, which is equal to neta ST by S tau CL alpha t. And that is nothing but CL delta E. It's neat and clean now. Okay? So what is this CL? This CL is of the whole airplane. Okay? This is very, very important, and you should understand this. And we know that we can easily calculate this. And by sign convention also, you know, if I put delta E down, which is positive, there is additional delta CL here. So CL delta E is sign wise, it is greater than 0. Clear? Okay. Once CL delta is clear, we will now go to CM delta E. Now we will talk about CM delta E. Let us see, this is the line, and this is your tail, and this is the elevator, symmetric tail. Let us CG somewhere here. As I deflect it, there is a delta CL, and this distance is LT, tail moment arm. LT is tail moment arm. So as there is a delta E deflection which is positive, it will give a delta CL upward, and about CG this will give a pitching moment downward, nose down, or it's a CM negative, right? So that is why this CM is because of this delta E. So this d delta Cm by delta delta E sine is less than 0, or we write Cm delta E is less than 0. So one understanding. Now what is the expression for Cm delta E? It is very simple. Cm delta E will be nothing but Cl delta E into the moment arm. Moment arm is Lt, but it has to be non-dimensionalized with chord Lt by C. And here is a minus sign. Why minus sign? Because we know this sign convention is given by us. For a positive delta E, there will be a negative pitching moment, which I already explained. And this, if I put the expression of Cl delta E, I find this is St by S, then Lt by C, tau into Cl alpha t. And we have defined St by S into Lt by C, or C bar. This is called tail volume ratio. So this is minus neta into Vh tau into Cl alpha t. What is important here to see? That if I want to increase Cm delta E, I have option like for a given, let's say, aerofoil tail, I can increase the value of Vh because it is St into Lt by S C bar. What I can do, either I increase St, tail area, or I increase Lt, or I can increase them in combination. So that is why tail volume ratio plays an important role, not only in stability as you have seen, but also for control, elevator control. Okay, so this is, I thought I must revise this. You should not get lost into the expression, equation, etc., etc. You must finally understand what are you going to do. We have also done another thing in terms of control, where we have derived an expression delta E trim, or required, whatever you write, is delta E naught plus d delta E by dCl trim into Cl trim. And we also seen that d delta E by dCl trim is equal to minus dCm by dCl fixed, stick fixed, by Cm delta E. In an approximate manner, we have neglected few terms, and this is nothing but minus xCg minus xn or xn naught or xnp, whatever notation you are using. This is the neutral point divided by Cm delta E. Right? I can write it as xnp. Please check what notation I am using. This is basically neutral point. And by now you know neutral point is that xg location at which dCm by dCl will be 0. Right? Now see here. If I suppose this is the airplane. Okay. So leave it. Suppose CG was here, and let's say neutral point is here. And if I now start moving the CG backward, let's say I ask the passenger, go backside. Okay? If I do that, or maybe heavier cargo I am shifting backward, what will happen? This xCg minus n naught, whatever term is there, this gap will reduce, right? And that will give a particular value to d delta by dCl trim, and you could easily see that if I go on reducing this separation, right, then the d delta by dCl trim also will go down. That is, if they coincide, this value will become 0. And you can see the other way also. If you see the xCg minus, this is a negative number, right? Because statically stable. So negative, negative, positive. Here, this is also negative. So this whole value is negative. Repeat. This is negative, and there is negative sign. So this value is negative. And what I am seeing, if I now plot, delta E versus Cl trim, what will be the slope of this line? slope is given by this, and this we have seen that this sign will be negative because this is the neutral point is aft of CG because statically stable. So this number is negative, this number is negative, and here there is a negative sign setting. The slope will be negative. So you'll see that. And what about delta E naught? Let's see. So I understood that d delta E by d CL trim sign wise this is negative. What about CM naught? CM naught is positive, and delta E naught is CM naught minus CM naught by CM delta E. So what happens? This is positive, this negative sign is here, CM delta is negative, so delta E naught is greater than 0. Correct? So we have seen delta E naught greater than 0, delta E naught greater than 0, and d delta E by dCl trim is less than 0. So the graph will be something like this. See, slope is negative and delta E naught is positive. Delta E naught is somewhere here when you touch it here, right? So let's say this is for a particular XCG location. Right? Now you are moving the CG backward. So what will happen as CG goes backward? As you have seen, if CG coincides with neutral point, this value will become 0, the slope will become 0. So as I am going towards neutral point, the slope will go on reducing. And at some CG location, this line will be at CG equal to x and p. This is a neutral point, but this line will be parallel to the x-axis here, and that is the point which is a neutral point. So one message you are getting, as I am moving the CG backward and backward, the slope is going to be flattened, right? Now, if that is the truth, what is additional information you can get from it? Let us discuss on that. Let us again revisit. We have become expert now in delta E and CL trim. Right, let's say this is the one graph for particular CG location. You by now know that the slope d delta E by dCl will depend upon static margin, and therefore it will depend upon XCG location for a given configuration, because N naught will not change, the neutral point will not change because of CG, right? Let us see here, suppose I ask a question, can I trim the airplane at this CL1 or not? Let's say this value is maybe 0.8. Immediately what we will check? For trimming the airplane at 0.8, how much elevator is required is given by this value. Right? Now somebody asks, can I trim it here? And you draw here. Then this is the delta E value required. How long or how far you can go along this axis? Who decides that? Suppose you can really generate CL very high, but please see that there is a limit of delta E deflection which is governed by delta E max. That is, delta E anytime should be less than delta E max. Why? Because if you deflect the elevator too much beyond certain angle, the flow will separate here. It will not be effective at all. And typically for normal case, this you will find between 20 plus minus 20 to 25 degrees. So beyond that, you will not be able to operate the elevator for a conventional airplane. In fact, it is 15 sometimes you will find. That is primarily because beyond that, elevator will lose its effectiveness. So what is the delta E max for the elevator will also decide how much CL practically you can trim. That means I have to go to reverse direction. Suppose limit is minus 15 degree, then I go like this, I come up, I say only this is the CL max I can trim. If delta E max is 10 degree, let's say 10 degree this is, then I say this is the CL max I can trim, because now my elevator is not effective beyond 10 degrees. Okay? If somebody says your elevator will be effective up to 25 degrees, let's say minus 25 degrees, then I go to this graph cut here, so I can trim it much higher CL. So this is the relationship between your delta E required and CL for a given static margin. We'll also try to have another understanding from delta E versus CL trim graph, delta E versus CL trim. Remember, this is CL trim. And you know the slope is negative. Let's say this is for XCG1 configuration. And let me also write that this is XCG1 and after, there is XCG2. And let's say neutral point stick fixed is here. And this is the reference line. Now for same airplane, if I move the CG to XCG2, and let's see that the graph looks like this. One thing we understand, because XCG2 is closer to neutral point, the static margin is less, it is less statically stable, the slope will flatten out, right? Now I want to check, if I want to trim the airplane at CL star, I'll say relatively what will happen if I try to trim the aircraft at CL star using XCG1 configuration or XCG2 configuration. Where do I need more elevator? So if I'm using XCG2, you see, I need this much of elevator, I say delta E2. If I am trying to trim for a CL star for XCG1 configuration, then I have delta E1. Which one is more? Definitely, delta E1 is greater than delta E2 as far as absolute deflection is concerned. And also we know that static margin in case of 1 is greater than static margin for case 2. Because the slope here is more, so it's more statically stable than XCG2 configuration, which is obvious because XCG2 is closer to neutral point than XCG1, and this distance we define as static margin. This also talks about the degree of static stability, right? So what is the message you are getting here? It's telling if stability, static stability is more, which is like SM1 greater than SM2, then control deflection to trim at a given CL trim is also more. So we say the pilot find it difficult to trim. If that stability margin becomes excessively high, he may not be able to trim it or find it difficult in trimming it unless you carefully design it. Okay? So this also establishes the relationship between control and stability. And we know that if an airplane is highly statically stable, then it is difficult to control. That means to change from one trim to another trim, you have to give very large deflection, elevator deflection. In that sense, we say more stability means more control effort. Okay? And to really increase the maneuverability, that's why we reduce this gap to bare minimum so that efforts are less. In fact, most of the fighter airplane will find the static margin is negative in a sense. It is marginally unstable, statically unstable. So this is the connection between stability and control. This you must keep back of your mind. I hope I have now made it clear, and you as a flight stability and control person should revisit this again and again and get that feel into your mind. Okay? Thank you.